So now we'll be taking a little detour from our course of reservoir engineering. We will be seeing a little bit of dimensional analysis. Okay. So dimensional analysis is a method which describes a natural phenomena by a dimensionally correct equation among certain variables which affect the phenomena. Like when a force is applied on a body, it accelerates. To describe this phenomena, we use the Newton's second law of motion. F is equal to ma. That means force is equal to mass into acceleration. Here we already know the equation. But one way of checking if this equation is correct is to prove that the dimensions of the terms on the LHS and is equal to the dimension of the terms on the RHS. So in LHS we have force whose dimensions are m, l, t to the power minus 2. And in RHS we have mass multiplied by acceleration. So you can see the calculation, and finally we get m, l, t to the power minus 2 for LHS also. Which is equal to RHS. So we know the equation is dimensionally correct. Okay, so dimensional analysis can be used to reduce the number of variables in an equation and arrange them in dimensionless groups. Dimensional analysis has one bottom line principle, the principle of dimensional homogeneity. It uses the dimensions of the variable affecting the phenomena, variables affecting the phenomena. So we know that the magnitude of quantities is different for different units, but the following four quantities have been found totally independent of each other: mass, length, time, and temperature. So these quantities are called fundamental quantities, and the dimensions of these quantities, that is m, l, t, and for temperature it would be k. K is for Kelvin, the SI unit of temperature. So m, l, t, and k, these are called the fundamental dimensions. Okay, and these quantities are called fundamental quantities. So they are prescribed by initial international standards. The units of other physical quantities are determined by their definition or by laws describing them. The symbols of fundamental quantities are mass is described as L, length is described as L, and T is described as T, and temperature is described as K. M, L, T, and K are dimensions of mass, length, time, and temperature respectively, or also known as the fundamental dimensions. Some physical quantities and their dimensions are listed in the table. You can pause the video and read them if you want to. Okay. Because most of them are associated with the fluid flow. Okay, in fact, this four-dimensional analysis has been presented from a fluid mechanics point of view, but they are also good for our purpose, which is the fluid flow through porous medium. So you can pause the table and read this table for a minute if you want to. Okay, and then click play. So Fourier gave the principle of dimensional homogeneity. The principle states that an equation of quantity is dimensionally homogeneous if its form is independent of the units of measurement and the dimensions of the variable or group of variables on the LHS is same as the dimensions on the RHS. Okay, so for example, P is equal to rho into height is dimensionally homogeneous because both the dimensions of pressure and the dimensions of dimensionally homogeneous. It is valid for all systems of unit SI, FPS, MPS, etc. Actually, it should be rho GS. This is a typing error. Okay, so the dimensions of P are ML minus 1 P. However, if rho is replaced by 1000 in the equation, P is equal to 1000 H is non-dimensionally homogeneous. It is only valid for P in kg per meter square and H in meter. Okay, so P is basically the weight force. Okay, it's like pressure divided by acceleration due to gravity. Okay, so empirical equations are valid only for one system of units. They are not dimensionally homogeneous. Dimensional analysis is most powerful tool in deriving equations for certain physical phenomena which cannot be derived analytically and must be solved experimentally. So by the use of dimensional analysis, we can get maximum information from minimum experiment. So let's say there are n variables used to describe certain phenomena. The assumption made in the application of dimensional analysis is that there are certain variables that affect the phenomena, let's say n minus 1. Then the last one is the dependent variable, depending on the n minus 1 independent variables. All variables other than these n variables have no effect on the phenomena and hence will not be in the equation. Like I just said, the total number of variables influencing the phenomena, influencing the problem, is equal to the independent variables plus 1. The plus 1 variable being the dependent variable. Dimensional analysis is generally used to obtain a functional relationship between dependent and independent variables. So step 1 is to decide which variables enter the problem. How to decide these variables? Well, for that, first we need to have a thorough understanding of the problem. But sometimes there are phenomena which are more complicated. For that we need to make some judgment calls. Okay, and that is a matter of experience. Okay, so what we'll be doing now, we'll be deriving Darcy's law. So as we saw while discussing Darcy's law, that it is an experimentally derived law. It is an empirical law. There is no analytical derivation of Darcy's law. So we will derive Darcy's law by using the dimensional analysis. Okay, so we know that for flow fluid through porous media, it depends on V, that is the velocity of flow, then K is the permeability, mu is the viscosity, and dP by dl, which is the pressure gradient. Okay, so the dimensions of these quantities are listed. So for V it's LT to the power minus 1, so 0, 1, minus 1. For permeability, its length square, okay, so 0 to 0. For viscosity, it's 2 minus 1. And for pressure gradient, it's 1 minus 2 minus 2. You can check it from the table. Okay, these are given in the table. So we assume, and now here we assume V, the flow rate, to be the dependent variable, and K, mu, and pressure gradient to be the independent variable. So we assume V is equal to K to the power A into mu to the power B into dP by dl to the power C. So therefore dimensions of V should be equal to dimensions of K to the power A into dimensions of mu to the power B into dimensions of dP by dl to the power C. Okay, so now basically we are making a system of linear equations. Okay, so NLT V0 1 minus 1 is equal to A 0 to 0 plus B 0 to minus 1 plus C 1 minus 2 minus 2. Okay, we tabulate them, we get a system of linear equations. We solve this equation to get A, B, C is equal to 1 minus 1, 1. So hence V is equal to K to the power 1, so K by mu dP by dl. This is the Darcy's law, simplest one. Okay, so that was one way. Okay, so step 2 is generally the formation of dimensionless groups of variables. Okay, so there are two methods for dimensional analysis. One is the Rayleigh's method, in which the number of dimensionless groups is unknown. Okay, so Rayleigh's method is obsolete and is rarely used. Okay, so we just did what we just did for deriving the Darcy's law. Basically, that's the Rayleigh's method. Okay, but nowadays it's rarely used. We cannot use it for complex phenomena. Okay, and that's the disadvantage, not knowing the number of dimensionless groups well in advance. That's the disadvantage. The other method is the Buckingham pi theorem. Okay, in this method we know the number of dimensionless groups well in advance. Okay, so we will now be seeing more about the Buckingham pi method. Okay, so for Buckingham pi method, what we do is, for applying Buckingham pi method, we select m repeating fundamental variables out of the n variables. Okay, so if there are n variables describing the phenomena, in which one is the dependent variables and the other n minus 1 are independent variables, so we select m repeating variables. Okay, so by repeating variables, it means that these n variables will appear in each of the dimensionless groups. Okay, so the variable should be, means basically we'll be making combinations. Okay, we will show this with an example and you'll understand it better. but then there is certain criteria for selecting these n variables. Okay, uh, the variables should be selected such that they in combination contain m fundamental dimensions in the problem. Okay, now the fundamental dimensions are for mass, length, time, and temperature. However, temperature very rarely comes into play. Okay, so in any equation, if the dimensions mass, length, and time, the three of them are occurring, then m will be equal to 3. Okay, so keep it as a note that m is equal to number of fundamental dimensions that are occurring in the equation. Now there may be equations like for the equation of kinematic motion, v is equal to u plus at. Only two dimensions are coming, length and time. So in that case, m is equal to 2. Okay, for equations of motions, m is equal to 2. When mass comes in, we go into Newton's law. Okay, for such equations, m is equal to 3 because mass, length, time, all three fundamental dimensions are coming into the phenomena. So m is equal to the number of fundamental dimensions. Okay, and we will have to select m repeating variables in such a way that those variables implicitly contain the fundamental dimensions. Okay, so these m repeating variables are then combined repeatedly with each of the n minus m variables. So each combination yields a dimensionless group of a pi term. Okay, and hence we obtain n minus m dimensionless groups. Okay, so this is how we know the number of dimensionless groups in advance. N is the number of variables affecting the phenomena, and m is the number of fundamental dimensions in the equation. Okay, so we will have n minus m dimensionless groups, and we know this in advance. Okay. So for selecting the fundamental the repeating variables, that is a tricky part. So for the case of fluid flow, okay, the criteria is that this is the criteria for the first repeating variables is selected so that it represents the geometry of the flow. Okay, and then the second second fundamental variable would be something that represents the fluid properties, and then the third repeating variable will be the one characterizing the fluid motion. Okay, so like in this slide, it has been explained. For geometry of fluid, we can for geometry of the fluid motion, we can take the size and shape of the fluid passage or the moving body diameter, length, etc., etc. So basically, the length dimension will come here from the geometry of fluid motion. Okay, from this one repeating variable. Then those variables characterizing the fluid properties like density, viscosity, surface tension, elasticity, wave of pressure, etc., etc. So basically, so the fluid characteristic that would bring in the mass fundamental dimension m. Okay, the first one will bring the L geometry, then the characterizing the fluid that will bring in the mass, and then those variables characterizing the fluid motion, the kinematic and dynamic characteristics of the flow such as velocity, acceleration, discharge, or pressure, force, power, they will bring in the time. Okay, so the first one, this will most probably bring in the length dimension. The second one will bring in the mass dimension, and the third one will bring in the time dimension. Okay, since we are considering for fluid motion, okay, so temperature becomes irrelevant. Okay, so the convention is to select length dimension from the category A. Those were the three categories A, B, and C. Okay, so the length dimensions come from category A. Density dimensions as category E, density of mass, and velocity from category C, because velocity contains a time factor. Okay? The time is contained in velocity. So we will see two examples of application of Buckingham pi theorem. One we will be applying it on Darcy's law, and the second will be applying on radial differential equation. Okay. So Darcy's law in radial coordinates can be given by q is equal to 2 pi r hk by mu del p by del r. Rearranging, we get c mu by 2 pi kh del r by r is equal to del p. Okay. So at any particular time t during the transient state, okay, during the transient state only, when the reservoir appears to be infinite in extent, the equation can be integrated from r to what seemingly appears to be a boundary at infinity. Okay. So we will integrate the equation from r to infinity, and on the right hand side we will keep t at the point r at time t to Pi, which is the initial, which is the boundary pressure, which is supposedly present at infinity. Okay, so we'll get Q mu by 2 pi kh ln r to infinity is equal to Pi minus P r comma T. Okay. So let's see this ln r2. Now we will do dimensional analysis on this one. So let's start with Q. Okay. So Q has the dimensions of length cube upon time. So 0, 3, minus 1. Then mu 1, minus 1, 1 and LT. Then 2 pi kh. Okay, so it will have dimensions of length cube, L cube. So 0, 3, 0. And Pi minus Pr comma T is equal to 1, minus 1, minus 2, and at this term ln r from r to infinity, it's logarithmic term. So logarithms are always dimensionless. Okay, 0, 0, 0. Okay, so n is equal to 5. The number of variables governing the phenomena is 5. M is equal to 3. Pi is the number of fundamental dimensions. So the number of dimensionless groups will be n minus m is equal to 2. So ln r to infinity is dimensionless itself, so it can be one of the dimensionless groups. Okay, so we got one there. To find out the second dimensionless group, we need to first select 3 repeating variables, one each from category A, B and C. From category A, we select 2 pi kh. Okay, kh is known as the overflow capacity. Okay, from category B, we select mu, the fluid viscosity, which characterizes the fluid. From category C, we collect Q, fluid flow rate. Okay, so which characterizes the fluid motion. Okay, so for phi 1, we will get 2 pi kh A mu to the power B and Q to the power C into Pi minus PRT. Okay, these are the repeating variables. Okay, these are the repeating variables, and this is the non-repeating variables. Okay, so these repeating variables are combined with this non-repeating remaining variable. Okay, so, and phi 1. So this is and we want a dimensionless group out of these quantities. Okay, so that is why the coefficients are kept A, B, and C, and on the left hand side the dimensions are 0. Okay, so we will again make a system of equations and solve them, and we get A is equal to 1, B is equal to minus 1, and C is equal to minus 1. So one dimensionless group we get from Darcy's law will be phi 1 is equal to 2 pi kh by Q mu Pi minus PRT, which can also be written as PD, dimensionless pressure. Okay. So these are very important for well testing. Okay. So we are basically deriving, just derived dimensionless pressure, which is highly used in well testing. Okay. So then we will apply Buckingham pi theorem on radial diffusivity equation. So the radial diffusivity equation is 1 by r del by del r r del p by del r is equal to pi mu c square k. This should be del p by del t. It's a typing mistake. So k by pi mu c can be collectively denoted as diffusivity constant d. So the equation can be rewritten as 1 by r del by del r into del p by del r is equal to 1 by d del p by del t. It's correct term. Okay. So now we will again tabulate the dimensions of all the variables. Okay, so P will be 1 minus 1 minus 2, R 0 1 0, P 0 0 1, and D 0 2 minus 1. Okay. So n is equal to 4, m is equal to 3, number of dimensionless groups, n minus n is equal to 1. To find out the dimensionless groups, we first need to select 3 repeating variables, one from each category A, B, and C. So from category A, we select R, okay, the length dimension. From category C, from category B, we select B. Okay, use the diffusivity coefficient. Okay, and diffusivity constant. So from category C, we select T. So the dimensionless, now these are our repeating variables. Okay, they will be combined with the non-repeating variable, the remaining variable, which is T. Okay. So phi 1 is equal to R to the power A, D to the power B, and Q to the power C. Okay, we will again get a system of equations, and we will get phi 1 is equal to dt by r square, which is equal to kt by phi mu c r square, which can also be written as td, dimensionless time. Okay, so that was it. So what we did was we basically derived td, which is dimensionless time, td, which is dimensionless pressure, and we also derived rd, but where it is get lost. Where did you leave it? this will give, instead of infinite there was a constant some value, okay, some finite value, then it would have come as the form of radius r2 rw. Okay, it would have been a ratio of radii to radii, length to length, again forming a dimensionless group. Okay, so this was the first dimensionless group. Let's call it RT, dimensionless radius. Then this was the second dimensionless group known as PD, dimensionless pressure, and the last one was this one known as TD, dimensionless time. Okay, and in our next session on weld discipline we will be